Hello everyone, welcome to the lecture series on kinematic analysis of mechanisms using graphical methods 1. In this, we are studying instantaneous center method, relative velocity method and relative acceleration method. In today's lecture, we will see relative acceleration method for 4 bar mechanism. For 4 bar mechanism, we will first construct the velocity polygon and then we will learn how to construct the acceleration polygon and how to extract the information from acceleration polygon to determine unknown accelerations of various links. We'll make some assumptions here. Dimensions of all the links are known and angular velocity and acceleration of one of the links is also given. So take an example of 4 bar chain ABCD. Let us suppose that dimensions of all the links are known and the configuration diagram is drawn at some suitable scale. Angular velocity and acceleration of input link AB is given and link AD is a fixed link. So we'll follow these steps. First of all, configuration diagram is drawn. Then we'll construct the velocity polygon. Then we will determine unknown velocities from the velocity polygon. After that, we will proceed for drawing acceleration polygon, and then from the acceleration polygon, we will find out the unknown accelerations of the various links in the mechanism. So before starting with the velocity and acceleration diagrams, we will revisit the concept of circular motion because we are going to make use of this concept in this coming method. So we know that for each and every particle in circular motion, there is one linear tangential velocity which is perpendicular to the radius of rotation, whose magnitude is equals to r into omega, as well as each particle in circular motion will have two components of accelerations if it is rotating with non-uniform speed. First component is centripetal component, whose magnitude is equals to v square upon r, and direction is always along the radius of rotation towards the center of rotation. And second component is tangential component of acceleration, whose magnitude is equals to r into alpha, and the direction of tangential acceleration is always perpendicular to the radius of rotation. And the total acceleration of particle in circular motion is the vector sum of these two components, centripetal and tangential component. So in relative velocity and acceleration method, while drawing velocity polygon, we will plot the linear tangential velocity vectors of each link. And centripetal and tangential component for each link. Take an example of 4 bar chain ABCD. For any given mechanism, what we will consider? We will consider one link at a time, and for that link under consideration, we will assume that one extreme point or end point of the link rotates relative to the another extreme point. As in this case, let us consider link AB. For AB, assume that B rotates about A. Now when B rotates about A, it will have linear tangential velocity perpendicular to radius of rotation AB. So in velocity polygon, we will plot this vector which is perpendicular to link AB. We will call this vector as velocity of point B relative to A, whose direction is perpendicular to link AB and magnitude is equals to radius of rotation AB into its angular velocity, like this. This VBA will be perpendicular to radius of rotation VB. In this way, we will determine tangential velocity vectors for each of the links and add them using the rules of vector representation in vector polygon. velocity polygon. Now since B is rotating with respect to A, it will have two components of acceleration. First is centripetal component, whose magnitude is equals to v square upon radius of rotation AB, and direction is parallel to the radius of rotation or parallel to the link AB, and it is directed towards the center of rotation A, like this. If link AB is rotating with non-uniform speed, there will be one more component of acceleration called as tangential component, and this tangential component is always perpendicular to the link AB or radius of rotation AB, and it will act in the direction of acceleration alpha, and magnitude of this tangential component is equals to radius of rotation into angular acceleration of that link. We'll plot these two acceleration vectors using the rules of vector representation in acceleration polygons. Now let us begin with, we'll suppose that the configuration diagram is drawn to the given dimensions using some suitable scale. Now first of all, let us consider fixed link AD. Now for this link AD, we will assume that D rotates with respect to A. So AD becomes the radius of rotation of D relative to A. Now we will determine the velocity of D relative to A, VDA, which is equals to radius of rotation AD into its angular velocity. Now for link AD, since it is fixed, its angular velocity is 0, and so the linear velocity of velocity of D relative to A becomes 0. Now in vector polygon, we have to plot this vector representing VDA, whose magnitude is 0. Magnitude of VDA is 0 means the length of vector is 0. So it becomes a point. So we'll plot the first vector, which is having 0 length, which represents the velocity of D relative to A in velocity polygon in the form of a point. Now next we'll consider link AB, whose angular velocity is given as omega 2. Now for link AB, we'll assume that B rotates about A. So when B rotates about A, its linear tangential velocity VBA is equals to radius of rotation AB into omega BA. So this is the magnitude of this VBA. And direction of this VBA will be perpendicular to radius of rotation VB and will act in the direction of omega 2. So this is the velocity vector representing velocity of B relative to A. Now we will plot this vector of this length perpendicular to AB in velocity polygon using the rules of vector representation. Now for plotting this vector in vector polygon, we will only concentrate on the name of the vector. So this vector is for VBA, velocity of B relative to A in this direction. Out of these 2 points A and B, we have point A with us. Velocity of B relative to A, vector representing this velocity, must pass through points A and B. So we have point A with us, so we'll make this vector pass through A. Also we have seen that vector VBA is represented by vector AB. So A must be at the tail of the vector and B must be at the head of the vector. So we'll place this vector in the velocity polygon such that its tail lies at point A. So we have placed the vector VBA at A in this direction such that A is at the tail and B is at the head of the vector. We have seen this in last lecture. Velocity of VBA is represented by vector AB. So vector A to B of this length. Well, next We will take link BC. Now for BC, let us find out velocity of C relative to B. Means we are again assuming that C is rotating about B. So its linear tangential velocity VCB is equals to R into omega. R is the radius of rotation BC and angular velocity of C relative to B, which is unknown. So we don't know the magnitude of vector representing VCB. But we know its direction. Its direction is perpendicular to radius of rotation BC. And we also know that vector representing VCB will pass through points B and C. Out of these 2 points, we have point B with us. So we'll make this vector pass through B. So this is the direction of vector VCB, which is passing through B and C. The C is unknown, so we have point B. So we have drawn this line perpendicular to BC through point B in the polygon. Next, let us consider link number 4. That is link CD. For CD, we will determine velocity of C relative to D, which is equals to omega CD into CD. But omega CD, that is angular velocity of link CD, is unknown. So we cannot determine the magnitude of this velocity and hence the length of the vector representing VCD. But we know its direction. Direction of vector representing VCD is perpendicular to radius of rotation CD. And the vector passes through points C and D. So we have point D with us. So we'll pass this vector through point D. But still we don't know the length of vector because we don't know the magnitude of VCD. Now look here, this line representing VCB passes through point C. This line representing vector VCD also passes through point C. So point of intersection of both these vectors must be point C. So velocity of C relative to B and velocity of C relative to D. Now we have marked the arrows towards C because this vector represents VCB. So it must be vector B to C. And this velocity represents VCD. So this should be the vector DC. So C is at head of both the vectors. So this completes the velocity polygon for 4-bar chain. Now from this velocity polygon, we will determine the angular velocities of link BC and CD. So consider link BC. So angular velocity of link CB is equals to VCB upon radius of rotation CB. Now magnitude of this vector VCB is nothing but the length of vector representing VCB. So length of vector BC will give the magnitude of VCB. So we'll measure the length of vector BC, multiply it by the scale factor with which we have drawn this velocity polygon and divide it by radius of rotation or length of link BC to get the magnitude of angular velocity of link BC. Now what about its direction? You can see VCB is pointing downwards. That is velocity of C relative to B is downwards. So velocity of C relative to B is downwards. That means link BC is rotating in clockwise direction. That is C is rotating in clockwise direction about B. Or in other words, you have to rotate this position vector BC 90-degree clockwise to head in the direction of VCB. So therefore omega CB is clockwise. Now for link number CD, its angular velocity is given by VCD divided by CD. So magnitude of velocity of C relative to D is nothing but the length of vector DC into the scale factor divided by length of link CD will give the angular velocity of C relative to D. Again, DC has to be rotated by 90 degrees in counterclockwise direction to head in the direction of VCD. Look at this. CD about D has to be rotated counterclockwise 90 degrees so that it points in the direction of VCD. So angular velocity direction of CD is counterclockwise. So link CD rotates in counterclockwise direction, like this. Now we have completed the velocity polygon and we have extracted all the necessary information from it. We will proceed for acceleration polygon. Now for each particle rotating about the another one, or for each particle in circular motion, we have seen that there are two components of acceleration, centripetal and tangential component. And for each of the links AB, BC and CD, we have assumed that one extreme point rotates relative to the another. And for each of the links we have determined, or we have plotted the velocity vectors of one extreme point relative to another in velocity polygon. So each of these points will have two components of accelerations. Consider link AB, whose radius of rotation is length of link AB. Linear tangential velocities are into omega, which is equals to length of vector BA into scale factor. So centripetal component of B relative to A is equals to V square upon R. V square BA upon length of length of link AB. This will give the magnitude of centripetal acceleration of B relative to A. Tangential acceleration of B relative to A is equals to radius of rotation, that is length of link AB, into its angular acceleration. Now for link BC, its length or radius of rotation is length of link BC. And for link BC, we have plotted VCB, which is equals to length of vector CB into scale factor. Now centripetal component of C relative to B is equals to V square CB divided by length of link BC. Now we cannot determine the magnitude of tangential acceleration of C relative to B because angular acceleration of link CB is not known. Now for link CD, its radius of rotation is length of link CD. For link CD, we have determined VCD, which is equals to length of vector DC in velocity polygon into scale factor. Centripetal component of C relative to D is equals to V square CD divided by length of link CD in magnitude. Again, we cannot determine its tangential component because its angular acceleration is not known. So after preparing this table, we will get the magnitude of all the centripetal components. So these are the quantities which we get from velocity polygon. The magnitudes and directions of the unknown tangential accelerations are determined from acceleration polygon, which we are going to do now. Now let us determine the directions of centripetal and tangential components. We have determined the magnitudes of centripetal or radial accelerations. Now what about the directions? For link AB, we are assuming that B rotates about A. So centripetal acceleration of B relative to A, which is equals to this much in magnitude. When B rotates about A, its radial acceleration will be from B to A along the radius of rotation AB and towards the center of rotation A, FCBA. For link BC, FCCB, C rotates about B, so its radial acceleration will be directed from C to B. And for FCCD, C rotates about D, so its radial acceleration will be directed from C to D. This is FCCD. So magnitude of all these vectors is mentioned in the table and directions are mentioned in this diagram. We have to simply plot these vectors in acceleration polygon in the given directions and of this much amount of length. Now for tangential components, we have magnitude of tangential component of B relative to A only for link AB. So we have length of this vector only. FTBA is perpendicular to radius of rotation AB or link AB, and it is pointing in the direction of alpha. So alpha is given in counterclockwise. So FTBA will be perpendicular to AB and will be directed towards left. This is FTBA. Tangential acceleration of B relative to A perpendicular to AB and in the direction of alpha. We know the length of this vector, which is equals to AB into alpha BA, because alpha BA is known. Now for link BC, FTCB is unknown in magnitude, but we know that direction of FTCB should be perpendicular to link BC. So FTCB is perpendicular to link BC. Similarly for link CD, FTCD must be perpendicular to link CD. Now once we have determined the magnitudes and directions of all the vectors, we will construct the acceleration polygon using these vectors. So let us begin with, so consider fixed link AD. For link AD, which is not moving, its centripetal component vector will be a zero length vector. So this is zero length vector, which represents centripetal acceleration of D relative to A, which is 0. Tangential component is also 0 for fixed link. Now next, we'll consider link AB. For link AB, we'll plot the first vector FCBA of this much length and in this direction. And we'll place the vector at A such that A is at the tail of the vector. One thing you will always remember, that when I say FCBA, the vector is going to start at point A or it will end at point B. What I said, FCBA will start at A or it will end at B depending on which point is with us. Now we have point A with us, so we will start this vector at A in the given direction. Like this, we'll start the vector at point A in the given direction. Whose length is equals to V square BA upon AB. Now to FCBA, we will add its tangential component. And we know that tangential component is always perpendicular to centripetal component. And to add the vectors, we have to place the vectors tail to head. So we'll place FTBA tail to head with FCBA so that it gets added to FCBA. Like this in the given direction. This is the direction of FTBA. We have picked up this vector and placed such that it gets added to FCBA. We have placed it tail to head. Now resultant FBA will be represented by vector AB. So this point is nothing but point B. FBA is represented by vector AB. So this is point B. Now we have done for link AB, we have plotted both these components, added both these components to get the resultant FBA. Now for link BC, we'll plot this first component, centripetal acceleration of C relative to B, whose magnitude is known, V square upon BC, and its direction is like this. So we'll pick up this vector and placed at point B, and while placing we will see that the known point B is the start point or end point. Now read this vector FCCB. B is the start point of the vector. So we'll start this vector at B, and to it we will add its tangential component FTCB, which is unknown in magnitude but known in direction. So we'll pick up this vector and add this vector to FCCB. We don't know its length, we don't know its direction, whether it is going upwards or downwards. So we'll draw this line of arbitrary length perpendicular to BC. Now moving towards the next link CD, we'll plot the centripetal acceleration of C relative to D, whose magnitude is equals to V square upon CD. So we know the length of vector FCCD and its direction is like this. So we'll pick up this vector and place it in the vector polygon. So read the vector FCCD. Which point is known? Point D is known, and point D is the start point of this vector. We'll pick up this vector and place its tail at point D. So this is FCCD. Now to FCCD we will add its tangential component FTCD, which is perpendicular to length CD. So we have added FCCD to FTCD. FT is always perpendicular to FC of, but we don't know the magnitude of FTCD also, so this vector is of arbitrary length. Now read this vector FTCD, this is passing through C, FTCB, this is passing through C, so point of intersection of both these vectors will be point C. So FTCB is now known in length and FTCD is also now known in length because we have got point C. Now resultant of FCCB plus FTCB will be FCB represented by vector BC, and resultant of FCBA plus FCCD plus FTCD will be vector DC, which represents FCD, total acceleration of C relative to D. So this completes the acceleration polygon. Now from this acceleration polygon we will determine the acceleration of unknown accelerations of the links BC and CD. First take link BC. From this equation, alpha CB is equals to FTCB divided by BC. BC is the length of link BC. FTCB is length of vector representing tangential component of C relative to B. This is that vector XC. So length of vector XC, which represents FTCB, will give the magnitude of FTCB. So length of vector XC into scale factor with which we have plotted the acceleration diagram divided by length of link BC gives the magnitude of alpha CB. Now what about its direction? You can see this vector XC. Tangential acceleration of C relative to B is pointing in downward direction. We'll go to that link BC. Tangential acceleration of C relative to B is pointing in downward direction. So angular acceleration of BC is clockwise. Or we can say that we have to rotate the position vector BC about B in clockwise direction through 90 degrees to head in the direction of FTCB. So alpha 3 is clockwise. Now for link CD, its angular acceleration alpha CD equals to FTCD divided by length of link CD. So FTCD, magnitude of FTCD is equals to length of vector representing FTCD, which is equals to length of vector YC into the scale factor divided by length of link CD. Now position vector DC has to be rotated through 90 degrees in counterclockwise direction to head in the direction of vector representing FTCD. So F alpha CD is counterclockwise. Thank you.